In this lecture, we are going to finish our derivation of radiation from an arbitrary charge and current source. And so where we left off in the last lecture was now we have a form for the electric and magnetic fields, which depends on the second derivative of the electric dipole moment. So what I'd like to do is to switch them now into spherical coordinates. So the electric field as a function of r and theta and time is mu0 over 4 pi, that second derivative of the electric dipole moment, times sine of theta over r in the theta direction. The magnetic field turns out to be mu0 over 4 pi c, the second derivative of the electric dipole moment, times the sine of theta over r in the phi direction. So again, what you see is that the electric field or dependence on the magnetic field is just the speed of light. Okay, so now let's calculate the Poynting vector, S, which is 1 over mu0, the electric field crossed into the magnetic field. And so that turns out to be 1 over mu0 squared over 16 pi squared c, the second derivative of the dipole moment, times the sine of theta over r squared, and then I have theta hat crossed into phi hat, which is going to give us r hat. So now if we clean this up a little bit more, what we get is mu0 over 16 pi squared c, second derivative, sine theta over r, quantity squared, in the r direction. So the radiation now is going to be radiating out along the radial direction, which is a lot of the use of the word radius. Okay, so if we want to now calculate the power is the integral of the Poynting vector through a closed surface area, which in this case would give us mu0 over 16 pi squared c, all of this stuff squared, and we would have an r squared sine theta d theta d phi. So there is no phi in the equation. So the integral over the phi dependence would just give us a 2 pi, and then the r squareds would cancel. So that's going to cancel with that, and in the end, what we get is a sine cubed. So let's work that out. So therefore, I would get the power is mu0 over 16 pi squared c, 2 pi for the phi integral, the second derivative of the electric dipole moment, that is squared, and then I have an integral of 0 to pi of sine cubed theta. Okay, so now you can go look that integral up, and what you should get now is minus 3/4 cosine theta plus cosine 3 theta over 12 evaluated from 0 to pi. Okay, so if you plug that in, what do you get? You would get 3/4 minus 12 plus 3/4 minus 12. And when you work that out, you would get essentially 4/3. So therefore I get 4/3. So that cancels with the 8 and the 4. 4 divided by 8 gives you 1/2 times 3. So I said this right here gives you 4/3. And so then in the end, what you get is mu0 over 6 pi c, the second derivative of the electric dipole moment, that whole thing squared. So that now is our equation for the power of is the power from radiation from an arbitrary source. Okay, so next what I'd like to do is to now consider a particular case, and that is our oscillating dipole. So, for example, 11.2, the first one is the oscillating electric dipole. So we wrote the dipole moment as P0 cosine omega t. The first derivative of this would be P0 minus omega sine omega t. The second derivative would give you P0 another omega, and then the cosine omega t. So I would get minus P0 omega squared cosine omega t. Okay, so now if I put that into our equations for the electric field, which we started with right here in spherical coordinates, then what I would get for an oscillating electric dipole would be an electric field, which is minus mu0 p0 omega squared over 4 pi sine theta over r, and then a cosine omega t naught in the theta direction. For the magnetic field, what I would get is minus mu naught p0 omega squared over 4 pi c sine theta over r cosine omega times t naught in the phi direction, which is the exact same result we got when we worked out the very specific case of an oscillating electric dipole. So here we started from an arbitrary shape, came up with a general form which dealt with the second derivative of the dipole moment with respect to time, and with that we can apply that and now solve for something that took us essentially 45 minutes to solve previously. Okay, so what about for a single charge? So the second case we can consider is we have just a single charge Q, and the dipole moment, let's say, is Q, but now the distance that it's moving is time dependent. So it's a distance from the origin. So now what I'm considering is if we have our origin right here, and we have our charge Q, now this charge is going to be moving, let's say, a different distance d. So if this is d, now d is going to be time dependent. It's going to change time 1, time 2. So now we just have basically a moving charge which is changing this distance d from the origin. In that case, if we were to take the second derivative of the electric dipole moment, then what we would get is the second derivative of our distance d, which is an acceleration. So we would get q times the acceleration of the particle, of the charge, of the single charge. Okay, so now if we put that into our formula for the power for this particular case is mu 0 q squared a squared over 6 pi c. So now the power that you would have is basically, because we put in for the second derivative of the dipole moment, that's just qa, you square it, you get q squared a squared. This turns out to be something called the Larmor formula. Where he worked out the case of a charge that is moving its distance. Essentially, it's accelerating, and that acceleration is producing radiation. And so this is the power of the radiation that you should measure of this moving single charge. So to kind of think about what we've done in these set of videos looking at the radiation from an arbitrary source, is what we've done is we've essentially did a multipole expansion. So we wrote out the charge in terms of a monopole term, a dipole term, and then figured out what the radiation is from there. You could take it even further now and say, what if there is a electric quadrupole term and a octupole term, and each of those terms in the multipole expansion should in fact be related to radiation. So we've only looked at the dipole term, and you could get radiation from, like I said, higher order terms in the multipole expansion.